This is going to be a first in a series of videos where I look into my own research and explain my papers to you. So my research mainly focuses on looking at the electrical conductivity of nanostructures, and in recent years I've been focused on carbon nanotubes. So what I'm going to talk to you about today is a paper that I've had recently published in a journal called Carbon Letters, and the paper title is Size-Dependent Conduction Characteristics of Catalyst Multi-Walled Carbon Nanotube Junctions. So I'll put in a link below to this paper, and also how to cite this paper if you do want to use this in your own work or papers. And I'll make another video which really goes into the depth of what a carbon nanotube is, and this will just be part of my usual output of videos onto YouTube. So this work really focused on flowing electrons or electrical current from the catalyst end of a carbon nanotube into the main body of the carbon nanotube. So these nanotubes were grown in a furnace using an iron seed. So these are small nanoparticles of iron, and these act as a nucleation site for the carbon nanotubes to grow out of. So quite a few of our nanotubes have this iron catalyst cap on the end of it. So what we did is we used an instrument called the nanoprobe, which we have in Swansea University, and what it allows us to do is position probes or very sharp metal tips onto nanostructures, and above it is a scanning electron microscope which allows us to get nanometer resolution to be able to really position these tips precisely and making sure we do land on specific parts of nanostructures. So we landed one tip on the carbon nanotube at one end, and then the second tip we landed at the catalyst end, but not on the catalyst, but still on the tube, and we took some current measurements by sweeping the voltage from -1 volt up to +1 volt, and then from those we can calculate the resistance at different voltages. So we just use the equation resistance is equal to the voltage divided by the current, and current is often given the symbol I, so it's V divided by I. We then took that second tip, lifted it off the nanotube, and then repositioned it on the catalyst and did the same series of measurements. What we were expecting to see, and what we did see, was that when the tip was in contact with the catalyst, the resistance measurements were higher. And of course this makes sense. There's going to be a boundary between that catalyst and the carbon nanotube, or a junction, which those electrons have to overcome to get into the carbon nanotube, and this adds that level of resistance. However, when we started measuring the diameter of the nanotubes and the catalyst on the end, we started seeing some odd effects. So when the catalyst was much bigger than the nanotube diameter and reduced in size down to the size of the diameter of the nanotube, the resistance increase was fairly small. However, when the catalyst was smaller than the diameter of the nanotube, that jump in resistance became much higher, and the smaller that catalyst got relative to the tube, the higher the resistance became. So what we did was we looked at the shape of this IV curve. So normally in a material you expect the IV curve to be what's known as linear, or a straight line. So as the voltage increases, the current also increases in what's known as a linear fashion, so it's proportional, i.e. the straight line. However, when that catalyst was smaller than the nanotube, our IV curve turned into an S-shaped curve, and this is what's known as a rectifying curve. And as the catalyst became smaller relative to that tube diameter, the amount of rectification in this curve became greater. So this got us thinking about what could possibly be happening. So one of my colleagues has actually done work on zinc oxide nanowires with a gold catalyst cap on it, and has found similar results, and he then, with a former colleague, did some simulations and modelling of the system and found that when the catalyst was much smaller than the nanostructure they were attached to, you ended up with an effect called current crowding. So as electrons flowed into the nanostructure, they got bunched up and you ended up with a high concentration of electrons. So what you have to remember here is that electrons are negatively charged, and when you put two negatives together, they start repelling each other, and this is what's impeding the flow of current into the nanostructure. So what's happening in the carbon nanotubes is, because they are tubular in shape, so they have a hole in the middle, when the catalyst is smaller than the diameter of that carbon nanotube, the electrons try to flow in, and then they have to push out towards the actual walls of the nanotube and to the extremes of it. So you get the electrons having to, instead of just moving down the tube in the direction of the voltage, having to spread out. And this what's causing this current crowding. They're getting caught up as they move outwards. And then as the voltage goes higher, those electrons are getting more force applied to them, which pulls them down the tube and sort of dissipates that crowding effect. So this is what's causing this shaping of the curve. It's actually the electrons forming their own barrier to themselves, being moved through. When the catalyst is bigger or the same size as the carbon nanotube diameter, the electrons can just flow straight into the tube. They don't have to make their way out to those outer shells. So as again, I'll make another video which explains what multi-walled carbon nanotubes are and what I mean by these different shells. But hopefully these little images that I've got on either side of me will help explain where the electrons are going and where they're crowding, and you'll see that these are forming the barrier to motion. So the question is why is this important? It's certainly interesting from a scientific point of view, but can this effect actually be used? And we think yes. So in electronic devices, you often have to flow current into your electronics, and many electronic devices actually use the change in current flow and the type of current flow as their actual working method. So we think that if you can control your catalyst size, you can actually choose how your device operates. So this is work that we want to continue in the future. Anyway, I hope you found this video on some of my research interesting. I'll be doing more of these videos which cover more of my work on carbon nanotubes, and as you watch more of them, you should get more familiar with how conduction in nanotubes and other nanostructures works. And along with my other videos, hopefully you'll start understanding the science and seeing how research can be put together. So if you have any questions about this or any ideas, please put comments down below. If you like this video, please hit the subscribe button and hit the bell icon if you want to get notifications. And finally, if you leave a like, please do that as well. And also down in the description, not only will you find the link to this paper and the way to cite it, you'll also find links to my other social media.